Okay, welcome back to my channel, guys. My name is Ansar, your helping hand, and in today's video, we're going to be going through an exam question that has to do with the Central Limit Theorem and sampling distributions. So, this is an IFoA question, and I've gone through before why I think that going through the Institute and Faculty of Actuaries exams, why that's a good baseline for our stats papers. Okay, so I'm going to show you the question, give you some time, and then we're going to go through the answers together. Okay, so the question says, and this is from the 2017 paper, September exam, question 2. If you want to go and find the specific memo or the examiner's report, as they call it, you can just Google IFoA past papers. Okay, so the question is, assume that n independent random variables x1, x2, xn are observed, which all have the discrete distribution given by this thing over here, and define the mean as the sample average, as we usually define the mean. Determine the exact distribution for x bar for n is equal to 2, and then question 2 is determine the approximate distribution of x bar for n is equal to 50, including all relevant parameters, stating any assumptions you make. Okay, so I'm gonna let you do the question, and then you can come back and we'll go through the answers. Okay, so I'm assuming that you paused and you did the question, or you tried to attempt the question. So we're going to go and do question 1. So question 1 says, determine the exact distribution for x bar for n is equal to 2. So this is a sampling distribution question because we have a sample and we have a statistic. Our statistic is the sample mean, and we need to determine the exact distribution for our sample mean. So remember, an exact distribution means you need to give me basically the probability that xn bar or xn, they just call it x bar, the probability that x bar is equal to a for all a's, basically for all a's. You need to give me this formula over here, right? And you can either give it to me in a formula or in a table. I say give it to me, I mean give it to the examiner or the person marking a question, but essentially this can be given in multiple ways. You can you can do a formula, or the way they've done it over here is they have a table, right? Now, essentially, in order for us to answer this question, we need to look at what happens if we take two samples from this distribution, right? So essentially, we have two values, A1, or we have A, right? We have A, and then we have B. So these are two samples that we're taking from this distribution over here. So our A can be 1, and our B can be 1. Our A can be 1 or 2, 1 and 3, and basically you're going to list out every single possible combination that you can have for A and B, right? So 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3, right? These are all of the possible combinations that you can have when you take two samples from the random variable with the distribution above. Okay, so now we have all of the cases that we can have in terms of what our samples are. So now we might want to figure out, okay, what's our xn or our x bar? What's our sample mean? Well, when we've got 1 and 1, it's just 1. When we've got 1 and 2, it's 1.5. 1 and 3 is 2. 2 and 1 is 1.5. 2 and 2 is 2. 2 and 3 is 2.5. 3 and 1 is 2. And then 3 and 2 is 2.5. And 3 and 3 is 3. Obviously, to get this, we're just adding both of these up and dividing by 2, because that's what our sample mean is defined as. And now we're just saying, okay, what's the probability of this happening? Now, we're not going to really think about the sample mean because we don't have the sample means distribution, but we are going to think about if we take two independent variables, the probability of seeing the joint distribution between them. So the probability of seeing A and B, right, because they're independent, is just the probability of A multiplied by the probability of B. And we have those probabilities in the distribution. We have what the probability of getting a 1 is, then the probability of getting a 2 is, and the probability of getting a 3. So all we need to do is just multiply these probabilities out. And I'm just going to, for reference, I'm just going to say the probability of a 1 is 0.6, probability of a 2 is 0.3, and probability of a 1 is 0.1. So we can do all of these multiplications, and we're going to see that this is going to be 0.6, right, for A, whereas 1 and 0.6 again, so that's 0.36, and it's just going through all of these calculations, so I'm just going to quickly do it. So this would be 0.6 times 0.3, 0.18, 0.6 times 0.1, 0.06, 0.3 times 0.6, 0.18, 0.3 times 0.3, which is 0.09, 0.3 times 0.1, 0.03, and then 0.1 times 0.6, 0.06, 0.1 times 0.3, 0.03, and then 0.1 times 0.1 is 0.01. So now we've got all these probabilities here, right? And you can check that this is actually a distribution, because these are all the possible cases, right? These are all the possible outcomes. So these probabilities should all add up to 1. And if you go and do that, you'll see that they do. If they don't, please comment and make me aware of it, and I'll be sure to make sure that I correct myself. But I'm pretty sure that these are the correct probabilities. And so now, right, we have every single possible outcome of x bar, and we have the probability associated with it. So now we can do a probability distribution, right? So in the case where they have it here, the way they've got it, they've got all of our x values, right? So we can call this our small x bar values, and we can say, okay, what are the possible values that x bar can be? Well, it can be 1, 1.5, 2, 2.5, and 3. So we just have to go and write, well, that's 1, 1.5, 2, 2.5, and 3. And then this is the we just need to give the probabilities associated with these particular outcomes of our sample mean. So we're giving you the probability that x is equal, that x is equal to our little x bar. And now we just have to go and see, okay, what are the probabilities that x is equal to 1, right? What are all of the cases where x bar is equal to 1, and add those probabilities up. So x bar being equal to 1 only happens in this case, so that's going to be 0.36, right? X bar being 1.5 happens here, right? And here, so that's 0.18 plus 0.18, so that's also 0.36. Then when x bar is equal to 2, that happens here, here, and here. So we're going to add 0.6 plus 0.9 plus 0.6 again, which, if you do the math, comes out to 0.21. And then 2.5 is this over here, this case over here, and this case over here. So this is 0.3 plus 0.3, which is 0.6. And then 3 is the only case that we haven't covered, and that's 0.1. So now you can see we've covered every single possible outcome when we take two independent samples, right? We've covered every possible outcome, and we've covered every possible outcome for our x bar. So this is the exact distribution of x bar when n is equal to 2. And that's question 1. So question 1 is quite involved in terms of the calculations, but it's not really difficult in terms of understanding what it means. Okay, and obviously this is a valid probability distribution if these things add up to 1, which you can go and check, and I'm pretty sure they do because I've done this before. But anyway, we move on to question 2. Question 2 says, determine the approximate distribution for x bar for n is equal to 50, including all relevant parameters and stating any assumptions you make. So we could, if they asked us for an exact distribution, which thankfully they did not, for n is equal to 50, we could do this exact same thing where we've got 50 different possible options, and we have 3 different options for each case. So you would do this massive table, figure out what the value of your x bar is, figure out the probabilities, and it's not difficult in terms of the understanding, but it's difficult computationally and you need a spreadsheet. So instead we go, okay, well, how do we get around this? Well, we can use an approximate distribution. So remember that the CLT says, right, that the limit as n goes to infinity of root n x bar minus mu over sigma squared, where this is mu is the expectation of any of your xi's and sigma squared is the variance of any of your xi's, then this thing will be normal, standard normal, when n goes to infinity, right? So that's what the central limit theorem says, that n has to go to infinity. But using the central limit theorem, so by the central limit theorem, by CLT, right, when we take our as n gets bigger and bigger and bigger, this value is going to look like a normal distribution. So we can say that when we take square root of 50, because that's our n value, and we take xn bar and we subtract the expectation of any one of our independent samples, and we divide. Oh, this is actually divide by the. Sorry, this is the This is meant to be the divide by the standard deviation. So this is just the square root of any of the things. So we take the variance of any of our values and we take the square root. That will be approximately normal, right? And that's what the central limit theorem allows us to do. It says once you get large and large enough n's, this particular value is going to look like a normal distribution. It's going to look approximately normal. So then we can go and find out, okay, well, what is e of xi? E of xi, and this is kind of a throwback to, I don't know, first year prob stats, but when you have a discrete random variable, you're summing over all of your i's, and you're taking xi, and you're multiplying it by the probability that xi is equal to i. Oh, actually that should be I, right? So essentially what you're doing is, in this case over here, you're going to take 1 and you're going to multiply by the probability that you get 1. Add 2, multiply by the probability that you get 2. Add 3, multiply by the probability that you get 3. So this is just going to be 1 times 0.6 plus 2 times 0.3 plus 1 times, times plus 3 times 0.1, which, if you work it out, comes out to 1.5. So we have the expectation. Now we need the variance in order to get the standard deviation. And the variance of xi, using the formula that we had whenever, is just the squared expectation, the expectation of the squares minus the square of the expectation. Okay? And in the same way that we would do a normal expectation to the first power, an expectation to the second power is just we square all of these terms here, but we use the same probability. So that's going to be 1 times 0.6 plus 4 times 0.3 plus 9 times 0.1. And we don't square that, because we square the inside and we subtract whatever our actual expectation is, which is 1.5, and we square this expectation. So when you go and work this out, this will be equal to 0.45. Okay, so now we have the variance, we have the expectation. So then using the central limit theorem thing, right, we then know that 50 times x n bar minus 1.5 divided by the square root of 0.5 is approximately normal 0.1. And now, in order to get this xn bar, right, we need to actually reverse our standardization. So here we've standardized it to be a normal random variable. And if you don't remember, if you have some y that's normal mu sigma squared, then z being equal to y minus mu, sorry, that's a bit horrible, over sigma is normal 0.1. So when you can kind of just match these things up, right? Where here, this z over here, z is equal to x bar minus 1.5. And then, obviously, we're multiplying by this 50, but we can just move it to the bottom. to be equal to the square root of 0.45 divided by 50. So now we can see, okay, well, our standard deviation is sigma, and in this case it's the square root of 0.45 over 50, and our mean, is 1.5. So therefore, by the central limit theorem, and it's important to use this by the central limit theorem statement is because they're saying include any relevant stating any assumptions you make in the question. So the assumption is that we're using the central limit theorem. We can say that x bar is approximately normal with mean 1.5 and variance is just the square of the standard deviation, so it's going to be 0.45 over 50, which when you calculate is 1.5 and 0.09. Okay, so that's the end of this question. If you have any questions about how I answered it, please put them in the comments. Don't forget to like and subscribe, and yeah, I'll see you in the next video. Cool beans, bye.